It's never been done before. I can guarantee you we'll create a crack in materialism with this. First of all, who I am, I'm not a physicist. I'm a CEO of a VR game studio. This is some of the games we make. So we make video games in virtual reality. And I always been interested in consciousness. I think materialism makes no sense. I truly believe in larger consciousness and that we are dissociated units of consciousness in a virtual reality. I have a background in math and physics, though. I studied that at the university. And when I stumbled on Tom's video and his Kickstarter to make the experiments, I was like, wow, this is amazing. I want to be involved into that. So I decided to pledge the highest amount possible and get involved with Tom working on the experiments. So as an entrepreneur, I like to start things. So I was like, okay, Tom, I'll help you. I'll contact a bunch of universities, and I'll help you make the experiments happen. So that's what I did. So today, I'll talk about the experiment that we've done that was never done before, the challenge to get these experiments running, the setup that we ended up with, which is entangled photon. Then I'll give a mini physics course, talk to you about the experiential results, the interpretation based on of textbooks physics, and finally, what we have in mind for future experiments. So as Tom just showed, the experiments that we want to do that was never done before is that we have a double slit. And you know that when we have a double slit, it creates an interference pattern. And the idea is to detect the which way data by which slit the photon with a particle went. So the detector D1 or D2 are on, but we don't record it. So we detect it, but we don't record it. So R1 and R2 are off. So that's the key experiment. It has never been done before. Most experiments that do that, they detect and they record on a computer, so you can look at the data afterwards. So it's the first time that someone did really clear experiment where you detect the which way, but we don't record. And the question that we were asking here is, does making the information accessible to a conscious observer makes a difference in that case? So that's the original vision that Tom had. I have to say that there are similar experiments that has been done in the past. So there's the delayed choice quantum eraser from Scully, Marlon O. Scully in 1999. One of the most popular one, you probably heard of that one online. There's a lot of videos. Another one from Wellborn in 2001. But these experiments, even if they're similar in the types of experiments, they never detected without recording. They always detect and store the data on the computer. So the implementation that I suggested to Tom, so by the way, first of all, I started contacting a bunch of universities, hiring physicists to help me in this project, and they told me, it's going to be super hard. Like, do you know that 2022 Nobel Prize winners are guys who did these experiments like in the 70s? Like, it's not simple. Maybe it's simple when you do a diagram on a PowerPoint, but like actually do it, it's going to be a lot of work. So I was like, oh, let's do it anyway. So just to show you what we built, so this is a normal double slit. We have a source. We are sending photons, individual photons, to two slits. And by the way, the photons they go one by one. We don't like the laser is not that precise. So some photon hits the top of the slit, the middle. Some goes to slit A, some goes to slit B. But we send them one at a time, and they reach here a screen. And in fact, in reality, we always say, oh, it's a screen, but in reality, it's not a screen. It costs way too much to have a screen that big. In reality, it's one detector, like D1 here, that we move with the motor at different positions. So if we run the experiments long enough, we move the detector on all possible positions, and this is how we measure over time, over many, many photons or particles, we get the pattern here. So if we just do a simple a double slit experiment with photons here, we get an inference pattern. So the setup, and I'll explain the details. You don't need to understand everything I'll say at this point. That's the goal of the presentation. We decided to modify this experiment by adding polarizers. So a bunch of polarizers. Basically, the polarizers here are used to mark the which way data. So we have different polarizers at each slit. And use also entangled photons, so entanglement. So everything is entangled. So we use a BBO crystal here that creates another photon that goes in the upper path. And that photon will be used to save the which way data. I'll talk about it later. And we know in that case that since in the upper path we can know the which way data, it will destroy the interference pattern because we know the which way data, and we'll get a particle-like pattern, so a diffraction pattern instead. So this is well-known physics. And the experiments, how to implement Tom's idea is that, let's say we have a switch here. So right now, in that case, in the upper path, we will detect the which way data. So the switch is set to record. But if I flip the switch and I unplug the cord, so I unplug the cord between the detector D2 and the database, then we detect, but we don't record. Okay, so that's how we suggested to implement Tom's vision. By the way, this is one implementation. We could do other ones. That was the cheapest and the simplest, but it took 5 years and a lot of money. Okay, so the experiments is basically do this. So we know this result. What happens when we unplug the cord? So we detect, but we don't record. Can we recover the interference pattern? So that's the idea here. Can we recover the interference pattern if we don't record? So that's the setup. So again, at this point, I just work with some physicists, help me design this experiment. We're like, oh, it's not that simple. It's a simple diagram. Sorry, it's not that hard. It's a simple diagram. We can do this. No, it's way more harder than that. So by the way, this is what it looks like on an actual optic table. So this is the actual experiment being done. It's not impressive per se, just a bunch of mirrors and detectors on a big optic table. But it took 5 years to do this. First of all, the first challenge I encountered, just a short story, it's the C word. When I start calling universities to do the experiments, and I was talking about consciousness and Tom Campbell experiments, they were like, no. We do physics, we do quantum optics, we don't want to hear about consciousness, we don't want to be involved with consciousness, so we don't want to talk to you. So that's basically the answer I got from many universities. So I came back to Tom and I said, I think we should approach universities differently. Maybe we should approach them by saying, we want to do a quantum mechanics course. Like we'll do a website where we'll do a pedagogical build-up of simple quantum mechanics experiments that will become more and more and more complex, and that will lead to this one, to this experiment that we want to do. But initially, it will be presented as a pedagogical build-up leading to this. So for scientists, we're not talking about consciousness, but they will do the experiment anyway. So that's the first challenge. That took many months to figure out this approach. And when we switched this approach, we were able to sign a university to work on it. After that, we wanted to do it with electrons. Like Tom said, it's really hard to detect electrons going through slits without affecting them, without touching them. And it's really more expensive with electrons. So that's why we went with photons. Photons are a particle of lights, by the way, so you send individual particle of lights. So we went with photons. We did it in California and in Canada. I'm French-Canadian, by the way, so we worked with the university in Canada and Farbod in California. So we did the experiments in 2 universities with the same results, so it was replicated. The other challenge that I did not expect is the university administration. So even when they are on board, you convince the researcher to do it. Just having the paperwork signed and like having the space at the university, and then the professor is busy with a bunch of stuff. They don't do this full time because for them this is like just normal science. They don't. We're not talking about consciousness or anything. So they're like, oh, we'll assign some a PhD student to work on it, but we need to wait like 5 months for the PhD student to sign some documents and be ready and blah blah blah. It was a pain, like it's a non-stop pain from university administration, but we went through it. Then, when we have everything aligned, the other challenge is equipment and calibration. So it looks simple here. Oh, we put a mirror, a detector, and stuff like that. But in reality, when you do it, if your detector is like just 1 millimeter or half of a millimeter off, it screws the experiment. So you need to recalibrate. Everything needs to be perfect, like no wind, no one like you're walking around in the lab and just touching the table. It will mess everything up. So really hard. And the other thing is the equipment is super sensitive. So sometimes the laser was a little bit too strong. We burn a lens. Then we need to order a lens. It takes like 2 months to order a lens because they're back order. We get another lens. Again, a lot of pain, a lot of pain. Finally, when everything works and we press, like, let's do the experiment, don't forget we're sending 1 photon at a time. So we're sending 1 photon at a time. It takes 24 hours. We need to let this run, the light close in the lab for 24 hours to get like 1 measurement of the experiment, like enough photons to be able to see a pattern. 24 hours. And you know, in universities, in 24 hours, it happens, a lot of things happens. You know, some doors are closed, sometimes there's an alarm during the night or whatever. All of this create noises in the experiment, and again, mess up the results. So think about it. Like the researcher needs to align the mirror, move this, blah, 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 press record, go to sleep, go back to university to discover, oh, the mirror was wrongly aligned. Oh, the laser was too strong. We just burned the lens. Oh, let's wait another month. So ton of fun, ton of fun. So that's why it took 5 years. I just wanted to show you what we went through to make this happen. But we did it. We did it. And now, for the future experiments, it will be way easier. We have contacts. We know all these challenges. And we've shown we were able to do it. Tom talked about a website. So this is what we pitched to the universities anyway. We said to them, we'll do a pedagogical build-up of 7 experiments from something super simple leading to Tom's experiment. Tom's experiment 1 out of 5. So the website, we have a preview here. It contains an introduction on the measurement problem. It contains experiment 1 about polarizers, single slit, double slit with polarizers, entangled photon pair, putting all this together. Also, then doing the delayed choice quantum eraser, which is what has been done by other groups in the past. And finally, experiment 7, which is detect which way, but don't record, which is Tom experiment 1. And finally, we have a conclusion and interpretation. So today, what I will do in the next 20, 30 minutes, I will go through all of this, basically a summary of the website to explain you the result, and hopefully you'll be able to follow quite well. I think I made it quite simplest I could. And the website is in construction. The URL is here. It's still in development, so it's not the official URL. Right now, it's testing-reality.webflow.io. If you want to visit it on your phone, just take a picture and visit it. And honestly, it's going to be the #1 source of information about double slit experiments and delayed choice quantum eraser. No doubt. No doubt, because I know I tried to get information about that myself. It doesn't exist. It's like in super deep textbook, super complicated, not well explained. So CUSAC will be publishing this website. And it will really be the #1 source to learn about quantum mechanics, to teach about quantum mechanics. So a bunch of universities and colleges around the world will use this resource. So good job, CUSAC. And on the website, by the way, I can't show it here right now, but there's simulators. Like this is a simulator. You can move around the polarizers, remove a slit, add a slit, and you see what the math and the theory says. We have the data, we have the raw data that we collected, the calculation, the math, the lab equipment, all of it. Like any question you have, it's there. So I'm really proud of the work we've done. It's not done yet. If you go on the website, still the text. Don't judge the, the text. It will be done by the end of the year and published officially. Okay. It's time for a mini physics course. So I try to make it short and sweet. Are you excited? Okay. Me too. First of all, polarization of light. So light is excitation of the electromagnetic field. So the electromagnetic field is a field all around, like all over the universe. There's one electromagnetic field, and this field gets excited, and this is what we call light. It's excitation of the magnetic field. It moves around in the universe, and a photon is a localized excitation of the electromagnetic field. So when light travels, it oscillates in the electromagnetic field. So it oscillates in a certain direction. It can be in a direction like vertical, horizontal, diagonal. It can even be circular. There's a bunch of different types of polarization. And you can polarize light using polarizers. This is polarizers. You can think about it like a window with the lines in it. And when you send photons through it, only what gets out is just photons polarized, so oscillating in the direction of the polarizers, outside of the polarizer. So light can be polarized. Normal light is in every direction. Polarizers allow you to have like only one direction. That will be important for the remaining. Okay, so first experiment that we have on the website is polarizers. And it's already very strange. It's really strange, just that part. So we have a source of light sending single photon, one photon at a time. And then we have a 45-degree polarizers. This means that what gets out of that, it's only photons oscillating in diagonal like that, 45 degrees. So it's oscillating 45 degrees. And we have a detector D1. So let's say we activate the laser, and the laser shoots photons, individual photons, let's say for 5 minutes, okay, just 5 minutes. So we let the experiment run, and we get a number of detection at D1. So I'll say we have 100% detection at D1. Now, we add the second polarizer. This time it's at 0 degrees. So the oscillating photon at 45, they reach a 0 degree. So the lines of the polarizer are horizontal. So what gets out? We will have less photons because the photons were oscillating 45 degrees, and they reach a horizontal. So only half of them will go through. So that's why if we run the experiment for 5 minutes again, we'll get 50% photons at D1 for the same amount of time. And what's important here, why 50% less? It's because there's a 45-degree difference between the two. So we went from 45 to 0. If we went from 0 to 90, so it's perpendicular like that, when it's perpendicular, no lights, the lights get completely blocked. If I shoot horizontally polarized photons to a window like that, nothing can get out. So this is what we see here. So the photons went through the 45, then the zeros, and then they're polarized at 0. When they reach the 90, nothing gets through. We get 0 detection if we let the experiment run for 5 minutes. So far, so good? Yeah, okay. So what's really interesting now? Okay, so polarizers are filters. There's always less light that gets out from a polarizer. What's really interesting is that if we add the third one, but in between, if I add a 45 in between, I get more light. So I'm adding a filter, and suddenly we have more light. How is this possible? When I try to wear like 5 sunglasses on my face, adding a 6th one in the middle don't make me see better. Okay? So that's really weird. And by the way, just for information, I could have put a minus 45, so the opposite, and I would get the same result. And I'll just have a video here to show it. You can do this at home, by the way, if you want to. You can buy these polarizers like for $10 on Amazon. It's not one photon at a time, but it shows the same phenomenon. So here we have 2. Now we show. I don't want sound. No sound. So here we have a 0 and a 90. So you see, you don't see light between the two. But if I insert a third one in between, there's more light that appears. So this is that case here. So you can see it in action. It's weird. It's really weird. It looks a little bit magical, even when you look at it. You can pause it. So what's weird is that this works with one photon at a time. This is what it looks, by the way, in the lab. It's not. It's a way more expensive. I'm sure you get the point. So it works when we send one photon at a time. So this means what this means is that when we send, we have a laser here. No. So when I send a photon, let's say the photon goes through the 0. When it gets out of the polarizer at 0, now the photon changes its state to 0. So when a photon gets through a polarizer, it transforms itself into a new polarization. So there's a probability to get through it or not, but if it gets through it, it transforms. So this is how we explain the light here. We went from 45 to 0, so we had a 50% chance of going through it. Then we went from 0 to 45. We also, again, get a 50% chance of getting through it. And then from 45 to 90, we also have a 50% chance of getting through it. So 50% of 50% of 50% give 12.5%. But when we just go from 0 to 90, we have 0% chance. So that's why adding a third polarizer adds a transformation to the photon that allows more lights to get through it. And this is really a property of quantum mechanics. The photon transforms its quantum state, and this process is truly random. It's truly random. So just there, it's already very weird. Anyway, so this is the basic for the polarizer. Now, double slit. Keep that in mind. I'll come back to this. So if we have a single slit, so this is a single slit. We always talk about double slits, but I was curious, like, what's a single slit about? So a single slit, if I just open one hole in a wall. By the way, I always have a 45 here. We don't care about this one, just to say that the light is polarized diagonally. So I send photons one at a time. Keep in mind that the laser is shooting a bunch of photons one at a time. Most of them hit the walls, but some of them go through slit A and then reach the detector here. And this is a graph of the number of counts that we get. So we get a lot of photons in the middle here, less on the sides. So this is the pattern that we get when we do it. This is an actual camera in the lab. It looks like that. So we see a brighter spot in the middle, and then we have less counts. And as you can see, basically we get a bunch of photons, a bunch of detection in front of slit A. And we call that pattern a particle-like pattern or diffraction pattern. If I do the opposite slit, it's the same. It's just that the lump is in front of the other slit. Okay? So that's it. What's weird now in quantum mechanics is that if we open two slits, we don't get two lumps. We get three lumps and spots where we don't have light anymore. And we had light before. So again, we open more holes, we get less light. Very weird. So anyway, that's the traditional double slit, but it's already super weird. And the explanation, by the way, the explanation that quantum physicists say is that the photon went through both slits at the same time. So a single photon gets to two slits at the same time and then interfere with itself to get this pattern. Don't forget that this is just an explanation, okay? So this is a theory. We don't know what really happens. We just know that when we run the experiment, we get this result. But no one knows what happened in between. So quantum mechanics is a theory that explains this interference. So I won't go deeper on the theory, but this is the result that we get. So now we say, okay, that's weird. Let's try to better understand by which slit the photon went through, because it's too weird. I mean, the photon needs to go through only one slit. Why both? So we'll use polarizers here. We are adding polarizers, different polarizers, orthogonal polarizers, so 1, 0, 190 in front of each slit. And this is to mark by which slit the photon went through. Simply say is that if the photon goes through slit A, it will become polarized at 0 degrees. Because remember, when a photon hits a polarizer, if it gets through, its polarization is transformed into the polarization of the polarizer. So if it gets through slit A, it will become polarized at 0. If it gets through slit B, it will become polarized at 90 degrees. So when we mark the slits like that, we lose interference. So as soon as we mark it, we lose interference. And scientists would say, oh, this is because now we differentiated the two slits, so the photon cannot go through both slits at the same time and interfere with itself. So that's their explanation. But this is what you get. This is the data in the lab, and this is, again, the equipment in the lab. So now we will add, okay, yeah, sorry. So these markers allows us now to know the which way. How we do that? Just before D1, if we put a 0-degree polarizers, when we will get clicks here at D1, it means that the photon had to go through slit A, because it's impossible it went through slit B, because if it went through slit B, it would be polarized at 90 degrees, and a photon polarized at 90 degrees hitting a 0, we have 0 probability of getting a photon. So basically, by adding a P1 here, we can know the which way data. If we add P1, you see the little lump is in front of slit A. If we add a 90 degree, the little lump is it's in front of slit B. So basically, it allows us to know, the which way data. Okay, sorry, come like that. So 0. If I put 90, I know it comes from slit B. Now, what's even weirder? If we put a 45, when it clicks at D1, then we don't know anymore by which slit it came through, because it could have came from 0 or 90, so slit A or slit B. Both have 50% chance of getting through 45% polarizers. So when we put the 45, so then we don't know which way information again, we recover the interference pattern. And what's even weirder is that if we put a minus 45, and I'm sure not of you maybe have seen this pattern before, but it's very important. When we put a 45, we get normal interference pattern. At minus 45, we get the complementary interference pattern. So it's an interference pattern, but all the spikes are inverted. You see here the maximum here is the minimum of the other one, and vice versa. Oh, sorry. Okay. So here we erase the which way data, and we recover the interference pattern, but there are 2 ways to erase information. And that's a really good point that we'll talk on Wednesday. There's always 2 ways to erase information. This is really weird. Scientists would say it's more selecting than erasing. What they mean is that if we don't have the polarizer here, we get a lump like that. When we add the 45, we select half of them. We select half of them, and we get this pattern. When we put a minus 45, we select the other half of them. This is what the math says in the theory. And when we add the 2 patterns, we get the lump. So it's consistent with the math, and this is what we get in the lab. So far, this is quantum mechanics with double slit, but we are not at atomic experiment yet. So now I need to talk about entanglement. So entanglement, we can use a BBO crystal. It's called BBO crystal. When we send photons into a BBO crystal, it creates a pair of 2 photons. So here we really get 2 photons that are entangled. Entangled, according to physicists, means that they are linked in a non-local way, and they will have the same polarization. So the polarization will still be random. It's either 0 or 90, but they will have the same polarization, meaning that if we get a click at D1, when I put a 0-degree polarizer here, I will get a click at D2 at the same time, because it launched 2 photons at the same time. And since they have the same polarization, if it's 0 at the bottom, it's 0 at the top. I could have put 90, 90, would be the same. And this also means that if we have different polarizers, like 0 and 90, if it clicks at D1, it will never click at D2, and vice versa. So we get 2 photons with the same polarization. That's the only thing that you need to remember. And this is just, we can do it for all angles, but it doesn't matter. Okay, so now we put all of this together. So we start with the double slit that we know. This is the actual data. And now we are adding a bunch of components. So first of all, we're adding the BBO crystal. The BBO crystal, I'm not, okay. So we're adding a BBO crystal, which creates a bottom photon and an upper photon that have the same polarization. The upper photon, we just create a little path with a mirror. The mirror just allows to make a cleaner graph. So it all goes to the right instead to the top. So the upper photons goes to the top, and the bottom photon goes through the double slit like before. So we still get the same pattern. We still get the interference pattern like when we didn't have a BBO crystal. Oh, that's the wrong image. Anyway, okay. Now we're adding polarizers. So I'm adding these two polarizers to mark the which way data. By adding this, we lose the interference pattern. Same thing. And here, it was we lost it when we didn't have the BBO. Then I'm adding the 45-degree polarizer. But this time, we lose the interference pattern, but before we add one. So the difference here is that the photon in the upper path contains the which way data because it has the same polarization. So I'll show it in the next slide clearly. So for example, if in the upper path I put a 0-degree polarizer and we get a click at D2, then we know that the upper photon was polarized at 0 degrees. So if we also get a click at D1, we can deduce that the photon went through slit A. And same if we put a 90-degree polarizer, if it clicks at D2, we know, and it clicks at D1, we know it went through slit B. So all of this, sorry if it's complicated, all of this is the way to measure the which way data without touching the photon. It's by having a second photon pair, entangled photon pair, that knows the which way. So the only thing that you need to remember here is that the upper path knows the which way of the bottom path. And last thing I want to say before I conclude with this is that now we have two data sets, and it's really important. When we send photons, we get clicks at D1. We get a bunch of clicks at D1, and we save that in the database. Okay, this is the database. Separately, in the upper path, we get clicks at detector D2. That also goes in the database. So when we get clicks like at the same time, or basically with the same pair, we call that coincidence. So it clicks at both places. So this is why my graph here, and this is an important detail, the black line is all the clicks we get at D1. But then we can say, oh, I don't want to see all the clicks at D1. I want to see only the clicks at D1 that also clicked at D2 at the top. And this is the orange line that we get here. So as you can see, at D1 we always get the particle pattern. When we know it clicks at D1, at D2 upstairs, we know that it went from it came from slit A. Just the little lump is right in front of slit A, and slit B, the lump is below. You see. So now that we have that, we can do the same thing as before. What is in the upper path? We erase the information. So in the upper path, I put a 45. So now I put a 45. So then we don't know anymore the which way data. When it clicks at D2, the polarization, I don't know the polarization. It could be 0 or 90. And when it clicks at D1, I don't know either. So what we get here is that at D1, all the clicks, we get the black line. And then if I plot only the clicks at D1 that also click at D2, I recover the interference pattern. And this is the pattern we get in the lab. And again, if I do the opposite at minus 45, I get the complementary interference pattern, the second way of erasing. So even with this more complex setup, we get two ways to erase. Here, sorry. Okay. So here we got this particle pattern. when in the upper path I'm adding the 45, I select half of them in the interference pattern. And if I add in the upper path the minus 45, I select the other half, getting me the complementary interference pattern. And again, both sums to the orange line on the left. So same principle. Okay. Finally, we come up to the initial question. So now what we wanted to do is to unplug the detector. So what happens if in the upper path we know the which way? By the way, the blue line, I think I forgot to mention it, but it shows what we know, what we can deduce. So if it clicks at D2, we know that it went through SID B. But we unplugged it. We unplugged. So a conscious observer will never know. So when it clicks at D2, yes, it clicks at D2, but no one knows. We don't save it in the database. We still get an interference pattern. So we don't recover interference, strangely. And we even tried to put a wall. Instead of unplugging it, we put a wall. And by the way, we tried to put a wall before and earlier, never changed the result. So the conclusion of all of this, so all of this will be explained in details on the website. Hopefully, you were able to follow in my, to me it took 5 years and I'm still confused. So if you're a little confused, it's fine. But it's the best I could have done, I think, to simplify it. So the conclusion of this, so at the beginning we said that, okay, in the case that we know which way data, it destroys the interference pattern and we get a particle pattern. And the question was, if we don't record, so we unplug, so as you can see here, the little animation, if we unplug the wire, so no human will ever know the which way data, because we unplug the wire to the database, do we recover the interference pattern? And sadly, because I wanted the opposite, but this is science, sadly the answer is no. No matter what we do in the upper path, no matter what we do in the upper path, we don't recover interference pattern in this setup. So this is what we get. So what's the interpretation of that? So the textbook's physics interpretation is what Tom was talking about. What physicists will say is that we don't recover interference pattern because just the fact that the photon, the upper photon, knows the which way data is enough to destroy the interference pattern, even if a human don't have access to it. And why? Why they say that? They say that because they say the information is in the upper photon, then it goes through the 90-degree polarizers, it clicks at D2, even if we don't plug it. But they say the photon that clicks at D2, the detector D2 is matter. It is electrons, it is atoms, it is molecules. So it says the photon will be absorbed in D2, and its information about the which way data will be stored in the matter of D2. So even if it's not accessible to a human being easily, it's still stored in D2, even if it's not in the database. So they say, if we have $1 trillion and a lot of time, we could extract the information in detector D2. And work really hard, like with 1,000 scientists, to extract with super microscope the information in D2. And then we would get the which way data. And that's why we don't recover the interference pattern. That's their explanation, okay? So physicists say information cannot be destroyed. It was in the photon, now it's in the detector, and then the detector will interact with the universe, so the information will be stored in the universe and everything becomes entangled with everything. So the information now is stored in the universe forever. It will never be destroyed, and it could be, in principle, recovered with trillions and trillions of dollars, which we'll never do. So that's their explanation. I'm not saying that, this is just a theory again, okay? Remember that in the late 1800s, we thought that physics was complete, with Newtonian physics and everything. And we're like, oh, we understood everything. Just details needs to be fleshed out. And then 20 years later, quantum mechanics, general relativity, true Newtonian mechanics of the board, and it was a revolution in physics. So that's not because this is their explanation that it's true. Okay, it's their best explanation to explain this phenomenon. But yeah, so that's the results that we got. So sadly, we don't get yet the results that we are looking for, but it's still great progress. My point is the website, the contacts, the learning, the experiments that we did so far is great progress, and the next ones will be even easier to do. So I'll just conclude with the mysteries that remains and the next experiments. So many mysteries remain. Okay, even from the scientists, they have no idea, and they say it out loud. They have no idea. So first of all, this was Tom suggested experiment 1 out of 5. Okay, so there's more to do, and we performed it with entangled photons, not electrons. So there's a lot of variables here that we can play with. So more to come. The other thing is that scientists, there's something called quantum measurement problem in quantum mechanics, and it's a known problem. You can Google it on Wikipedia. No one has the answer. How can we have object in superposition, object at different places that are truly random, and yet when we measure, we see only one result in our consciousness, when the math says there's many results? So some physicists say, oh, you know, all the results exist at the same time. It's called a many world. So every time that the photon branches in 2 slits, it creates multiple copies of the universe. It's called the many world. Some believe in that. Some think it's too much. But there's no consensus. We have no idea. We really don't have. So Schrodinger's cat, you know, the cat that, as long as you don't look, it can be alive or dead at the same time. It's still an open question. No answer about that. Quantum mechanics interpretation has no consensus. So again, despite a century of debate, no consensus. There's the many-world interpretation, there's the consciousness collapse interpretation. So still a lot of questions there. And finally, the other problem of consciousness still has no answer. So I still think, and I truly believe, that Tom's explanation, which is also shared by many other philosophers like Bernardo Kastrup and others, that consciousness is fundamental and that we are altars in that larger consciousness system, is the best explanation still. But so far, the experiments that we've performed are not able to prove or disprove that. That's the point. So, my conclusion, what can we do next? So I have a very ambitious program of 5 experiments that, not even experiments, but like 5 fields that I recommended to explore to show a crack in materialism. So that's really the key. Why are we doing these experiments? It's to show that materialism is false, or there's an issue with materialism, to open minds of scientists and everyone. So that's the goal. So the experiments that I suggest, yes, there are some in quantum mechanics, but I also think that we can go outside this to bring evidence to scientists, which is not quantum at all. So keep pushing for a revolution of science. So the 5 experiments that I recommend, so there's quantum mechanics. So do more quantum mechanics. So experiments, so that's the first one. So continue with the experiments that Tom suggested. Do more with electrons, but they are more complex, more expensive, will take more time. There's another thing is that to create a quantum consciousness contest essay. Consciousness is less and less taboo. That's the right, I think with people like Tom and other philosophers, they're bringing, and there is one here and everyone, all the speakers here, you know, talking about consciousness. Now it's less taboo and more scientists are willing to talk about it and work on it. So why not do an essay contest to bring all the community of scientists with a big prize pool to submit essays about quantum consciousness and figure out maybe new ideas of experiments. The other one is ESP, you know, extrasensory perception and psychokinesis affecting the, you know, parapsychology experiment, like the ones that are done at IONS, or things that you can experience at Monroe Institute, and I'm sure that a lot of you have experienced. So we're doing extraocular vision research. I'll talk about it in a minute. And as a video game designer, I have a super idea to do parapsychology experiments at scale with millions of players. I'll talk about it in a minute. And finally, and I think most importantly, because we already have a lot of evidence of these things, it's just that scientists don't want to look at the data because they say It's just impossible in materialism. I just don't want to look at the data. So I think we need an inspiring worldview. Tom is pushing for it. A lot of people are pushing for it, but I think we need to step up, and I like to be ambitious. I think we need to step up at another level. I think we need another Matrix-like movie. You know, mass appeal, even better than the Matrix, to inspire a new generation of people to think outside of the box. So why not try it? So I'll just have one slide on each, and I'm done. So more quantum experiments. So first of all, there's Tom suggested 4 more experiments. There was one to predict quantum random events. I won't go into details, but like there was one with a microprocessor to predict a beam splitter or a decay of a radioactive process. We can do it with electrons, with like light measuring coils to do a light measurement on the particles. There's also something called interaction-free measurement. You can do, it's Eliezer Weinman that invented that. There's a way in quantum mechanics to measure things without touching them. So I think maybe we could try a double slit where we detect the which way without even measuring it, without even touching it. Of course, it will be more complex, more expensive, but there's something here. And the most expensive one is to try to erase information with a black hole. So I don't think I will be able to do that one, but would be interesting. If anyone has contact with the black hole makers, call me. But the key point here is that with the experiments that the experiments that we got, the contacts, it's going to be way, way easier. It won't take 5 years to do more experiments. That's the point. We'll be more efficient. Quantum consciousness essay contest. So this is just a preview of it. So I have a friend, double postdoc in quantum information, working with the best on the planet, with the inventor of the quantum computer, and with the inventor of the quantum teleportation, like really high-league quantum information people. So Tom just approved that we start working with him to organize an essay contest to bring up the community of researchers around the world, amateurs and professional, to submit essays and potential experiments to test the link between consciousness and quantum mechanics. So this will be moving along, and hopefully we'll have even new ideas and new experiments to be done next year. Extraocular vision. This is new to me, but I think this one has something special. I don't know if you are aware of that, but there's more than 20 schools around the world, teachers and schools who claim, and there's thousands of videos about that. Tom also posted one on his channel, that people that are blindfolded who can see. So I haven't experienced myself, but I'll do it in the following months, hopefully. I know that some people here have done it and claim, and they genuinely claim that it's true. Either their children has done it or they've done it themselves. So be blindfolded and be able to read characters, see colors, see things like that. So I think, to me, this is the best paranormal phenomenon ever, because it's not something sketchy that it's hard to reproduce. Or if someone can read blindfold, that's it. Checkmate. Checkmate materialism. We just need one person, just one, that can read blindfold on demand and succeed, let's say, 60% of the time. That's it. Materialism is done. So when I stumble upon that, I'm like, wow, this is incredible. So right now, this is a video of blindfolded kids and adults. They're blindfolded, and they're driving go-karts. And there's thousands of videos like that. And like, what is this? Like, it's incredible. Anyway, so I'm really flabbergasted by that. Okay, you can pause the video. No one crashes, by the way. So right now, I'm working with Alex Gomez-Marin. He's a theoretical physicist and neuroscientist. He has 2 PhDs. He has also, is in contact with a blind person that is blindfolded and that can read. So I'm like, this is insane. It's incredible. And he won a prize from IONS. I don't know if the people from IONS Institutes are here with us today, but he won the prize of, it was $100,000 split among 3 winners. He won the prize for Seeing Without Eyes research proposal. So I reached out to him, and now we're collaborating to contact all the schools and ask them for their most talented individuals to reproduce this phenomenon in a controlled environment. And I mean, we will do this in the next 6 months. And if we have a couple of talented individuals that can reproduce this on demand, I can guarantee you that we'll create a crack in materialism with this. Because it's kind of simple to demonstrate. Okay, the most ambitious one, yeah, there's an even more ambitious one after that, but a more ambitious one is, this one here, we'll do it at the low scale, let's say with 20 people, 20 talented people that can do that. I was thinking, because we make video games, I'm with my chief operation officer here, Phil. We have a studio of 20 employees, we make video games, so I'm like, oh, we could combine our passion and create a video game, state-of-the-art video game, and this is just a mock-ups drawing, called Protocol Academy. So why not create a video game, a super cool video game, like Clash Royale or Clash of Clans, or name the biggest one, with nice graphics, nice gameplay. But what we do in that game is that we retest all the extrasensory perception and psychokinesis experiments that have been done for many years. From like people from IONS and different researchers. And we apply very rigorous protocols. So there was the Advanced Meta-Experimental Protocol, AMP, presented by the director of the Fetzer Franklin Foundation, who worked recently with Dean Radin to make protocols even more rigorous. So we work with rigorous protocol. We have a game here, a social game where we can move your character around, meet people, hang out, talk about consciousness, go to meditation seminars and stuff like that. And you can go play games. And when you go play games, you play games like telepathy games. So you're matched up with another player. You have cards presented to you. The other player has cards presented to them. And it asks you, pick a card. So I pick my card. And the other player needs to telepathically guess which card I picked. But the key here is that, these experiments normally when they're done in universities, they're done with like 100%, maybe 1,000. If we're super lucky, 1,000%. Here, let's create the best game on the topic, attract millions of players, and have millions of trials. So then we can say, are these people beating chance? Are they telepathically doing something that is beyond chance? And then we can even contact the individuals with the highest or strongest powers to do more experiments with them. So this was an example of game. Another example of game is that we could do, this is more psychokinesis. We have a player and you have 2 doors. You need to make a choice. And the choice that you make is based on a quantum event. So let's say we have a quantum number, random number generator. When you make your choice, let's say left door, we do a quantum measurement and we get a quantum outcome. And the outcome is either you win gems or whatever to buy you a new hat and continue in your levels, or you get a super scary monster, rah, and you lose a life. So this way, this is to see, can the player affect the outcome of a random number generator? So, because before opening the door, he has an intent of not being scared and winning cash. So when we do a lot of trials, we'll get more data on if it's possible against chance. So the game Protocol Academy, the idea is to can be a profitable game. We can even make money while making this game, creating a hub for people to collaborate, to connect, and output millions of data points, like never before in mankind, to show once and for all, or disprove, I mean, this is a legitimate science, that these phenomena are possible. So that's Protocol Academy. And the last one, again, super ambitious, but we'll do it, because why not? The Matrix is 25 years old, so why not do another Matrix for 2030? But this time, we do a blockbuster movie, with sci-fi and nice special effects and super deep philosophical story, like The Matrix. But the baseline is that consciousness is fundamental. It's like the baseline is that we proved that consciousness is fundamental. We prove that we're part of a larger consciousness system, and we write the story into this world. And we show what the world based on love and collaboration can lead to. We get an inspiring story and a great storylines, action sequence and stuff. And I think the timing will be perfect because right now we are in a crisis, climate crisis, a geopolitical crisis, AI will be a crisis too. It's cool and scary at the same time. And VR is coming along also. We're more and more in the virtual reality that we created for ourselves. So the timing is perfect. I think mankind, like where's the new inspiring sci-fi movie where we see that in 2040 the world is incredible? Where's that movie? It's always like apocalyptic movies and robots killing everyone. Like, I want something inspiring. So let's do it. Yeah. So my plan to do that, so the goal of this movie is to just put an image, inspire everyone, and inspire researchers and everyone to be more open-minded to these phenomena, to this research, to the output of what we will have done with these experiments and past experiments as well. And I'm from Quebec, Canada. I'm a French Canadian. Denis Villeneuve is a French Canadian from Quebec. He made the best sci-fi movies in the past, 10 years. Dune, Arrival, Blade Runner. So the plan is to let's write a script, a good script, pitch it to him, and let's make it happen. So, yeah. So for fun, just a quick timeline, because I'm an entrepreneur. I like to make things happen, so I need to set the timeline, deadlines, and goals. So Quantum Consciousness Essay Contest, it's starting right now, next week. It will take about 9 months to happen. This will lead to new quantum experiments with electrons, other stuff. We'll see how we can fund them. The extraocular vision thing, we're reaching all the schools right now. I'm confident that in 6 months, we'll have at least 10 individuals be able to reproduce these phenomenon and do a publication about it and make it a crack in materialism. Protocol Academy will take some time because we're working on full-time on our video games, but at some point, we'll sell our company and create Protocol Academy. So if ever you want to invest in that, call me. So we'll have millions of trials of people doing paranormal ESP and PK phenomenon at scale. And we'll start working right now on the sci-fi movie scenario and pitch it to Denis Villeneuve to produce it for 2030. So to get the ball rolling, I am raising $2.6 million. So more quantum mechanics experiments, they will be more complex. We can go faster because we know how now to do them. We can do 2 at a time, 3 at a time. Document all of this, but it will cost, I mean, these are rough estimates, but I think we need another $1 million if we want to bring this to another level. Quantum consciousness essay, it's more the prize pool. We organize it, we need a prize pool, so we'll open the prize pool for people to invest if they want to make the prize pool bigger, to attract talent. Extraocular vision, right now we're doing it. We'll have the 20 people that proves that they can do the experiments, but after that we need to publish and we need to replicate. So after that we'll need to open like a lab and invite people, train them and reproduce it. So I estimated $200,000. Protocol Academy video game, the best is to start with the prototype, not spend 100 million on that. So make one game, 10,000 users, trials, show that it works. So $1 million for that, including marketing, and the movie script for by the way, if there's writers, script, contact me. I would like to work with you on the script and iterate on it and pitch it to Denis Villeneuve. So that's it. I think.